function pointers are one way to gain a very powerful capability, and that is deciding at runtime what code to execute. And to a certain extent, you have that just with an if, right? If something or another, block of code, else some other block of code. But you get into situations where you want to sort of separate making the decision about what's going to run from actually running it. And in C, the only way to do that was through function pointers. You'd have some kind of an if that would set the value of a function pointer in a variable, which would wander around with you for a while until you went to use it, and then you would invoke whatever function you had set the function pointer to point to. Now, if you hear that problem description, it's normal as someone who's learned some C++ now to say, well, couldn't I just use polymorphism for that? You know, create the right kind of subclass if I have saving account, checking account, retirement account, whatever. Then I carry it around as a base class pointer, as an account pointer, and then call its update method, and the right code will run. Absolutely. That is a fantastic solution to that problem of different code running depending on the circumstances you're in. As well, you may be ringing a bell on lambdas and saying, aren't lambdas kind of a way for you to just to plunk the code you want to execute right there? If some condition, do this passing in this code for the second parameter, otherwise do this passing in this code for the second parameter? Sure is. Also another way to do it. In most cases, either polymorphism or lambdas are likely to be a better way to go. I still run into circumstances where I use function pointers, but less often. However, what I'm really all about in this module is helping you to read some really opaque, punctuation-rich code that you don't understand what it's doing. And function pointers definitely can fall into that camp. Now, setting and using them, especially if it's a global function, super easy. Take a look at this. I set some variable method, which I cleverly haven't shown my declaration of method, to a value. And calculate slowly is the name of a function. Now, if I had round brackets, calculate slowly, open round bracket, close round bracket, semicolon, I would be calling the function and putting the result into method. But that's not what this line of code is doing. It's actually setting the function pointer to point to the calculate slowly method or function. The next line, which has method at A, B, and C, will actually execute calculate slowly at A, B, and C. Now, of course, just like when we first did pointers, you know, if you say int I, int star pi is equal to address of I, and then star pi equals something, woohoo, that's just like saying I equals something. And you're like, so what? So it is here. These lines aren't very useful when they're right after each other. I could have just called calculate slowly and passed in A, B, and C. Where they become useful is when method doesn't get called right immediately after getting set, gets sort of carried around and used later. Now, to declare that function pointer, everybody uses a type def. It's a reasonably tricky thing. You don't want to be doing it repeatedly. So the type def says that changer is a pointer to a function that takes an integer called I and returns an integer. You sort of have to read them inside out. Now, once you've done that, then they're easy to declare instances. So I just say changer f. I have a file here called functions.h, which is included into my main. And I have a pair of global functions. These aren't member functions of any class. They both have the exact same signature, and that's vital when you're working with function pointers. The function pointers are typed. So a pointer to a function that takes an integer cannot be used to point to a function that takes 3 strings and vice versa, just as a pointer to an integer can't be used as a pointer to an employee or something. Both these functions take an integer and return an integer, and they're reasonably well named. Doubler takes an integer and returns double of that integer. Tripler takes an integer and returns triple of that integer. So far, so good. There's nothing function pointery here. I'm just creating things for the function pointers to point to. Then I have my type def. So this type def says that changer is the type I'm defining, and it is a function pointer. The combination of the star, which would mean pointer for anything, and the open bracket here is a function pointer to a function that returns int and takes a single integer. This may not be entirely logical. You may not particularly like it, but you can memorize it or look it up when you need it. This is the way to typedef a function pointer declaration. Then once you've done the typedef, life is pretty simple. Let's look at this change function. I declare a changer f. So f is a function pointer that can point to any function that takes an int and returns an int. And here I'm going to set f to either point to tripler or to doubler. And then I'm going to use f. So I triple larger numbers, numbers that are more than 5, and I double smaller numbers, numbers that are not more than 5. Let's go back to my main. I have I1 here who has a value of 7, and L1 who has a value of 3. 7 clearly is more than 5, 3 is not more than 5. So I'm going to call change and I'm going to pass in I1, which is 7. And I'm also going to call change and I'm going to pass in L1. And just to be on the safe side, I'm going to cast that long down to an int so that everybody really knows what's going on. So let's set a breakpoint here and run to this point. I can step into this function and as I step through it, you can see that I, that's the parameter I was passed in, is 7, and f is really not anything yet. In a debug build, that's a uninitialized memory. We go into the if because 7 is more than 5, and we're going to set the value of f, and the debugger actually understands that it's a function pointer and can show us that it's now pointing to tripler. So I step over again, and if I step into this call, you can see that I actually find myself inside tripler. Now, not surprisingly, 7 times 3 is 21. We can work our way back out. And you can see, if I just step over one more time, that I2 has the value of 21. We tripled the larger number. Here I'll just step over it to be a little bit quicker, and you can see that I3 has the value of 6. We only doubled the smaller number of 3. So that is how simple it is to use a function pointer once you have it set up. The typedefs are definitely your friend. This is a tricky piece of syntax, and what's worse, if you get it wrong, the error messages are a little bit opaque. So all of these round brackets are necessary. This pair of round brackets representing the parameters that are passed to the function, and this pair of round brackets highlighting that you are actually declaring a function pointer. The syntax I just showed you was for a pointer to a global function, a little handy utility like doubler or tripler. If you want to use a pointer to a member function, something that's a member of a class, it's a little trickier. First, when you set up the typedef, you have to name the class. A member function of the utility class that takes no parameters and returns an int is what's being typedefed here. And you wouldn't be allowed to use that pointer to point to a member function of a totally unrelated class like bank account that also happens to take no parameters and return an int. When you want to set the value, here we're declaring an instance of that typedef called action, and we actually use the address of, say, the address of utility : triplex. This is uglier than just saying the name of the function, as you saw when they were free functions, but it's actually less confusing for some people because now at least it's obvious why it's called a function pointer. We're using the address of operator, and we sort of expect to use that when we set pointers. That's how we set, integer pointers, and it was kind of weird that we didn't have to do that for free functions. When you want to use it, again, it's a pointer, so you dereference it. Now there's a lot of brackets here, and again, they're not optional. So first we reading from the inside out, dereference the pointer star action. That gives us what the function pointer points to. We want to say u dot that. That whole thing needs to be in some round brackets, and then we have another pair of round brackets where the parameters go. And this particular type def, as you see at the very top, this function doesn't take any parameters, so we have empty round brackets there. I have a class here called utility, who has this double X and triple X methods, has an X private variable constructor that sets the value of that X, and I either return double it or triple it. Inside functions, I have this manipulate utility function. It declares a local utility instance, in this case called u, passing in a number, sets up this function pointer, and then with a similar if that we had before, but just checking against 3, I'm going to set action either to the triple X or to the double X method. And then I'm going to call whatever it is that action points to. In my main, I'm going to pass in the value of 5. So since 5 is greater than 3, we'll expect to see it tripled, and we'll expect to see 15 come back as our answer. So let's run this. I'll step in. And again, you can watch in the locals window down here. Action is currently uninitialized memory. Since our value passed in is 5, we've built a utility using 5, and that's greater than 3, so we expect to set this now to triple X. That's exactly what happens, and you notice that the debugger is aware that it's utilities triple X and not somebody else's. Then when we invoke the method, we can step in and find ourselves invoking that method. Step out and out again. And I4 is 15 as expected. So member functions, a little bit trickier to work with than global functions, but still well within the realm of possibility. Come across when you're reading old code is the void pointer. You'll see it in function parameters especially. Oh, this function takes a void pointer. When a function returns void, that means it doesn't return anything. So you might be tempted to think that void pointer means a pointer to nothing. But what it actually means is a pointer to anything. A little bit like, say, an object reference in a world where everything inherits from object. In C++, there isn't anything that everybody inherits from. And so void pointers are used like that. You can take any kind of pointer and cast it to a void pointer successfully. And you can take a void pointer and cast it back to any kind of pointer you like without a runtime error. Of course, if it doesn't really point to whatever you've just casted it to, really bad things happen. So you'll see a function that takes a void pointer, and the first thing the pointer does is turn around and cast that to an employee star, whatever it thinks it points to, and then go ahead and start using member functions of employee, let's say, based on the fact that you've cast it to that. This is an extraordinarily dangerous behavior. There really isn't any runtime checking going on. If for some reason somebody passes an insurance policy pointer to this function, it's going to try to cast it to an employee pointer, then it's going to try to go ahead and use it as that. It's going to interpret the memory as though it was an employee object. And if it isn't an employee object, really bad things happen. So a much more type-safe approach would be, don't take a void pointer. If this function takes, any kind of bank account, then have it take a bank account pointer, a base class. And then you can use either polymorphism to invoke the right subclass method, depending on what subclass thing the pointer actually points to, Or you could use the static and dynamic cast that we've covered elsewhere to get it into being a savings account pointer so that you can call some method. The problem with void pointer is it just takes type safety, which is one of the best parts of C++, and throws it away and says, who cares? It's all just ones and zeros. I'll figure out what it is. And that's what we like to sometimes call enough rope to blow your foot off, to mix metaphors. C++ gives you a lot of control, and things like void pointer are a way to say, I'm the one running the show here. I'll do whatever I like. It can be a powerful technique, but it's such a dangerous technique that you really shouldn't be using it. I'll show you just how compliant things are and how little they complain while you do bad things. I'm calling here a function called useSomething, and I'm passing into it a series of different pointers. This one is the address of I1, an integer that currently holds the value 7. This one is the address of the member of the struct point, the X member. So if we just scroll up a little so you can see those values, right? P.X was set to 2. So I'm going to take the address of that piece of a struct. Then I'm going to take the address of the whole struct and pass that into useSomething. And then I'm going to take the function pointer, because when you just say the name of a function without the open and close brackets, that's a function pointer, and I'll pass that into useSomething. useSomething is obviously a very accommodating and happy-go-lucky kind of a function. Sure enough, it takes a void pointer. And what it does is, it's positive it's getting an integer. So it just takes that something and casts it to being an integer pointer, and then uses it. Now I'm going to do a fairly mild use. I'm just going to print it out onto the screen. There are a lot worse things I could do. So let's go in here and step over each of these in turn. So this is printed out 7, which is great. That I1 is 7. I printed out 7. This void star is looking like a pretty cool thing. And if I step over again here, remember P.X has a value of 2. So sure enough, there's 2 on the screen. So that's fine. They were both integers. Now what about when I pass in this whole point? You notice no errors, no exceptions, no badness. And it actually even prints out 2 on the screen. That's because it goes to the memory where the point starts and says, I know what you are, you're an integer. And then interprets the bits that it finds there as an integer. And the bits that it finds there are the first element of the struct, and they do happen to map out back out to the value of 2. But if anyone ever changed the layout of the struct so that something different was first, this would stop working. This is exactly the sort of thing that breaks code that uses void pointers. Now what about when I pass in this function pointer? If I hover over it, you can see that it has a numerical value. The debugger, however, is aware that it's a function. It even uses the little function symbol here. So I step over, no errors, no complaints, and a number prints out on the screen, which is the numerical address of that pointer. Super non-useful. If you're absolutely positively sure that you'll always be passed an integer, you can get away with void pointers, and that's why you'll see them in other people's code. But you see that if anybody uses it in an unexpected way, you just have no protection. I will point out that you do have to cast it. You can't ask the object to know what it is. So I'm just going to uncomment these lines and build. See, right away I have red wigglies. The motivation behind these lines is like, oh, something, you know what you are, so I'll just give you to see out and we'll be fine. And that's like a polymorphic way of thinking, which would be great if we weren't using void pointers. But we are using void pointers, and the compiler needs to figure out which of the many overloads in IOStream of this operator to use here. Is it the one that takes the output stream on one side and an integer on the other, or the output stream and a string, or the output stream and any other many number of kinds of types? And it doesn't know the type, and so it can't do that. Now here, when I've cast it over to an integer, it knows the type of this, it knows it's an integer and it can do it. So you can't get any kind of runtime goodness. You have to say, I believe that this is an integer pointer or an employee pointer, and I'm going to do the cast. That's the danger of a void pointer. You have to be sure that you know what it's really pointing to.